So density is going to be equal to mass divided by volume, right? Everybody hates to go to the DMV, right? Okay, so that is the easiest way to remember density, okay? Now you want to remember this equation. This equation is going to be very important. So anytime that you see the units, grams over milliliters or grams over cubic centimeters, that should immediately tell you what are we talking about? What are we talking about if you see grams over milliliters or grams over centimeters?
Density.
Density. Okay, so anytime that you see the units of mass over volume, you're probably going to need density, right? Okay. So we talked about ice and water. Here I showed you ice and water. Ice floats on water, where if we had a cube of ethanol, totally frozen, ethanol is drinking alcohol, and we put it in alcohol, it's not gonna float because it's not less dense than the liquid version or its liquid phase. It's just gonna sink to the bottom. And you guys can see that here at the bottom. All right, can you guys see my screen? Or am I just talking?
Yes, no, I can see it.
So let's talk about some other things in life that you encountered. How many of you guys go to rivers or to the ocean or?
I do.
Anything like that?
I've gone.
You've gone? Okay. So have you ever seen a piece of wood on the water? Or
Yeah.
have you ever thrown a piece of wood in the water? Or have you
Yes.
ever gotten in a boat?
Yeah.
What are most boats made up of?
Wood.
Wood. Okay. Why do boats float?
Isn't it because they're less dense than the water?
They're less dense than the water. So a lot of the wood that we use for boats are less dense than water. So they're going to float. And so you're able to float. It's not because you're less dense than water. It's because the wood there is less dense than water and it's able to proportion out the weight on it. Okay? A little physics going on there. So these are all of the density of common things that we run into. What was that? Hello?
No, I just had a question about that.
Sure.
So basically, you know, like when you're on the pool and then like you hold your breath or like you inhale a lot of air and you could float, but sometimes you don't float. So
Yeah,
how does that work?
that's because in those cases, you basically let out a lot of the air, right? So the air helps you float because it's less dense than water. So they always tell you, like, take a deep breath, hold your breath, right? And then so you're sucking in all that air, and so you're able to float for a while. But eventually what's going to happen is that you're going to let out all of that air. If you let all of that air, what are you going to do? You're going to start to sink. And have you guys ever put in a glass of water in the sink? And initially it kind of floats on top, right? And it's because the air in the glass itself is not solid glass, so it's not going to sink automatically, right? So initially you have occupied with air, but if you start getting a little bit of water in there and a little more water in there and a little more water in there, what happens? To that glass that's empty, that was initially floating on the top, you put a little bit of water in it, what happens?
It starts to sink.
It starts to sink, right? Because you're displacing the air, which is less dense than the water, with water, which is water, right? So it's just going to start floating down. And then you have glass and water, it's just going to sink to the bottom, right? Yeah, no, maybe. Okay, you guys kind of see that? See how it works?
Yes.
Okay, so these are some of the densities, right? And if you look at them, right? Look at the density of helium. Guys, have you seen a helium balloon?
Yeah.
Yes.
Yeah. So what happens to a helium balloon on a nice sunny day and you let it go?
It floats all in the sky.
It floats, right? Because it's less dense than air, right? So if we had a gas that's more dense than air, then it's going to sink. Where, you know, if it's less dense than air, it's going to float. Okay? Piece of cake?
Makes sense.
Okay. So here we have a mass of 50.00 milliliters sample of methanol. Let's see. Sorry. The mass of a 50.00 milliliter sample of methanol is 39.59 grams. Determine the density of methanol. So what are we going to use to determine the density? Bernardo, since you asked me a question, I get to ask you a question. What are we going to use?
I think mass over volume.
Mass over volume, right? So, oops. Oops. So density equals mass over volume. So which one is our mass?
39.59 grams.
And you knew that because?
Because grams is a type of unit we use to distinguish mass.
That is correct. You're like, duh.
I confused myself at first. I was like, wait, I'm doing this completely wrong. And then I remembered that.
Okay. And volume?
Would be the 50.00 milliliters.
Okay, what do you guys get?
0.7918.
Okay, how many sig figs should I have?
Four.
That is correct.
Two.
No, you're right.
Oh, it's four.
You said right at first. 4, you're right. You're not used to me saying you're right. You're like, yes, 4, you are correct, 4. Okay, piece of cake, simple.
Yes.
Okay. Okay, let's see. It says the density of a certain machine oil is 0.910 grams per milliliter. Find the volume occupied by 196 grams of that oil.
Yeah, these are the ones that I couldn't answer on the homework. I was
Okay.
hoping I could get help today.
Cool. So let's see if we can start since you brought that up. So what do you think we're going to start with? All right. What would you say is our given?
The grams to milliliter.
So you're saying this is our given? Or would that be more of a conversion or a equivalency?
Oh, so it's 96 grams, 196 grams.
Okay, so let's start off with what our given is, 196 grams. Now, what do I want?
Grams to milliliters.
Do I want grams to milliliters, or what does it tell me to find? What does it say right here?
Oh, grams.
It says find grams. Are
The
we?
volume.
We want to find the volume. So what is the units for volume?
No, find the volume.
What unit? What is the unit for volume?
Milliliters.
Milliliters. So we want our answer in milliliters. Okay, so we always want to start off with what we're given. Ideally, we don't want to start off with an equivalency, but sometimes we can't help it. Here we can help it, right? So how can I change these grams to milliliters using our equivalency? This is our equivalency boxed up here. You don't know? Look at it. It says 0.190 grams. What was that?
Grams divided by milliliters.
So if I put this at the bottom, right? Wouldn't that be exactly what you just said? Oops.
9, 10.
So what do you have if you have grams over grams? So G over G. What is that
They
equal?
cross out.
They cross out. Okay, so that means that this guy is going to cross out that guy. Piece of cake. And so all of these problems, essentially, all you want to do is use dimensional analysis, right? I mean, of course you want to think about it, but the goal is, hey, this is what I'm given. This is what I want. So always break it down to given and what you want, okay? So what do you guys get?
215 milliliters.
How many steak figs?
3.
Okay.
I have a
Piece of
question.
cake? You got a question?
Yes. So you know how the, density equals mass over volume? Can you
Mhm.
kind of like, because the way I did it is I just kind of,
Manipulated the equation?
yes, manipulated the equation to where I got volume equals mass over density. And then
Yep.
I got from there. Is that okay as well?
Yeah.
Do it like
Yeah.
that? We won't
Yep,
get points
no.
or anything.
So this is the way it works in real world, right? Do I care how you get your answer if I was your boss?
Hopefully not. As long as it's
Yeah, as long as you get to the correct answer and you're not blowing up my plant or you're blowing up my hospital or killing my patients, then I'm cool with it, right?
mm-hmm.
So how you get there, it doesn't matter. There's going to be 5 to 10 different ways to get to the same answer. Long as you can sit there and show me, and also so I can see if you've made mistakes along the way, right? If you just give me an answer, I kind of care because I'm not 100% sure that, that might be correct because I don't see how you did it, right?
Mm-hmm.
But as an instructor, you're not obligated to do it the way I do it,
Okay.
because there's multiple ways of getting to the same answer. Okay?
Gotcha. Thank you.
No problem. Okay. Okay, so that's it. That's it for this chapter. Any questions? Pretty simple.
Yep.
Okay. Let's see. What else did I want to say about this? While I'm looking, I need to talk to you guys about, everybody picked up their lab, right?
Yes.
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 Okay. Good, so I don't have to talk about it with you guys. Okay, so let's see. But if you guys have friends who haven't picked up their lab, tell them to go pick up their lab. Contact Tony, and he will help them. Let's see. What's her name? Melanie. Let's see. The 15th, which is today. Oh, it's too late. Why would they put it on a Monday?
It's 14.
Today's the 14th? I don't know what today
Yes.
is. I've been in the lab all week long, all weekend. Yes. Okay, so tomorrow, tell them tomorrow from 11 to 1, there will be another distribution for those who didn't pick it up. So if you know anybody who was like, weren't able to do it from 11 to 1, they'll be able to pick it up. Okay? Okay. Let's see. So let's go to chapter 5. Okay. So there's this guy named Dalton. Can you guys see my screen? Yes,
Yeah,
no,
we
maybe?
Yes.
Yes, okay. So there's this guy named Dalton. So, he was a scientist, and he came up with a couple of theories. And for the most part, because they're theories, for a lot of it held true. But I want you to sit there and think about these theories based upon what we know today, currently, okay? So it says each element is made up of particles called atoms. Atoms are indivisible. Do you guys know what indivisible means?
Unable to duplicate?
No, not unable to duplicate.
Unable to
To
break
divide?
apart.
Unable to break apart, that's right. So it can't be broken down into smaller parts, right? It says all atoms of one element are identical in every respect. Atoms of one element are different from atoms of another element. Atoms of one element combine with atoms of another element to form chemical compounds. Okay, so this is just a picture just kind of showing us, what he was meaning, right? So like the first one, he's just basically showing us that all of the atoms, they look identical. They're exactly the same, right? The next one was, an atom can't be destroyed or created. And that's with the hammer, right? And then this one is, all atoms of a given element have the same properties, including mass. And atoms of different elements have different masses. And then this one, this is just basically saying that, you could put two atoms together and they can make a compound. And depending on the ratio, you could end up with two different compounds, okay? Are you with me, Norma?
Yeah.
Yeah, good. Okay, so this is called the law of multiple proportions, or the law of definite composition. You'll see it named having several names. Basically what it says, and I'll just give you the gist, is so the ratio between two atoms, either the mass ratio or the number ratio of two atoms, are going to be consistent. So whether you have a little bit of it, or you have one of it, or you have tons of it, it's going to be the same. Like for instance, carbon monoxide. So for carbon monoxide, we have one carbon, one oxygen, right? If we looked at the mass, carbon weighs 12, oxygen weighs 16, roughly, right? So regardless of how much carbon monoxide, I'm always going to end up with the same ratio of one carbon atom to one oxygen atom, okay? Where carbon dioxide has a ratio of what?
Two to one.
2 to 1, right? 2 oxygens for every 1 carbon. And that ratio is always going to be the same, whether I have a whole room of carbon dioxide or I just have 1 molecule of carbon dioxide. The ratio is always going to be the same. Now, doesn't that make sense?
Yeah.
Okay. So often you'll see it because, like I said, it is, there's a couple of laws that they just kind of group together. Law of definite composition, law of multiple proportions, right? It essentially means the same thing. One just kind of looks at mass, the mass relative to each other. One look at the number relative to each other. Okay, so the electron. You guys remember what an electron is? I'm sure we talked about
It's the particles that are negatively charged around the shell of the atom.
that. The nucleus, you mean, right?
Yeah.
Yeah, of the nucleus. Yes, that is correct. So we know now, we didn't know it before, but we know now that the atom is composed of 3 parts, right? We have a proton, an electron, and a neutron. We know that protons have a positive charge. We know that electrons have a negative charge, and we know that neutrons have a neutral charge. Now, these are some things that you may not know, right? The electron is really, 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 really small and really, 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 really light. So let me give you an example or a comparison, similarity. So if I put a speck of dust on my shoulder, right? And let's say I weigh 220 pounds. So with that speck of dust, how much would I weigh now? If I didn't have it at first and then I just want a single speck of dust on me.
Same.
I'm gonna weigh the same, right? Are your scales so good that they can tell the difference between a speck of dust and 220 pounds?
Nope.
Mine aren't, you know? So I'm gonna weigh roughly 220 pounds, okay? So the electron is kind of like putting a speck of dust on a proton. Proton is going to be the majority of the weight. The proton is going to be, so like for instance, if a proton weighs 1, an electron weighs 1 over 1,837 of the mass of a proton.
That's tiny.
Yeah, it's really, really tiny, right? And so, but the thing is that, you know that like Napoleon was really small. Napoleon had a little bit of a punch, right? So that electron has a strong negative charge. That's equivalent to that proton's positive charge, okay? And so this was actually discovered by J.J. Thomson. This part, the electron itself, was discovered by them.
Are we going to have lab today?
You guys will have a simulation that's going to be due, but no, you won't have lab today. You guys have lab on Wednesday anyway, so.
Okay.
Yeah. That's if you choose to have lab on Wednesday. We will start the normal labs on the 21st or after the 21st. So, okay.
Okay.
Let's see. So, are you guys getting me so far about the electron? Okay.
Yeah.
So Thomson, the thing about Thomson though, he discovered the electron, but he couldn't quite understand the relationship of the electron and where the proton was at and everything like that. Jennifer kind of alluded to it earlier that, you had the proton in the center and your electrons are orbiting around it, right? But at that time, they didn't know that. So they just kind of thought it was like how you bake a cake. You just kind of throw everything in there and it happens to end up where it's supposed to end up. And there's no like rhyme or reason to how everything ends up. It's just kind of a pie put in together. Or in their case, what was very popular at the time was plum pudding, which is like a bread pudding. Okay, so he said, okay, if I throw all of these negative charges in there, there's going to be positive charges in there too, and they're all just going to mix up all nicely together, right? And that's what his mentality was. So Rutherford, carried away. Rutherford comes along, and he's like, nah, I don't necessarily agree. There has to be some more logic to this than what we think. And so he took a piece of foil, and it was a gold foil, and he basically aimed positive particles at this foil. Now, they're alpha particles, and they're all positively charged. And so he directed them at the foil. So what he saw was that some of them deflected off, but some of the positive particles went straight through. And so he was like, okay, so there's some deflection going on, and there are things that are going straight through. But he had noticed that there was like a pattern of that deflection, some type of order to that deflection. So that meant that there wasn't just this random mixing of plus and minus charges. There has to be some type of order, some type of structure. Okay, so after further analysis, he comes up with the idea that all of the positive charges are in the center of the atom, and all of the negative charges are circling the atom. And so this is, the orbital type model that we kind of live with now, sort of. Gets complicated.
Is there a
Okay,
reason
so what was that?
Is there a reason why he chose gold foil?
That is a good question. I'll have to look that one up. I don't know. I think, he was just kind of so just in general, most scientists were rich in the first place, or they come from wealthy families, because they can spend their time during this time period, of course. They could spend their time investigating things that were never known about. And a lot of the stuff that they did, the experiments they did, it would be based out of their own pocket. Or if they were associated with a university, but in all cases, they typically came from well-to-do families, rich families. And so he probably just had some gold foil laying around, just kind of kicking in. It's like, okay, I'm just going to try gold foil, because I have it like that, So. Okay, so this basically gives us what we call the nuclear model of the atom, right? And so what we said is that the atom basically has a nucleus that has a positive charge. And then around it, we have these electrons circling, okay? And the thing about it, the nucleus is really dense, and it is the bulk of the weight of the atom, and it's in the center, but it's going to be really, really small. And then the space that's being occupied is mostly empty, and that's going to be occupied by electrons, okay? So let me show you what it looks like, okay? So you guys see here that there's the nucleus. This here is the atom as a whole. This blue space is it's called the electron cloud density. And so it's like a dense cloud area, kind of like the clouds around the Earth, right? So like the Earth is mostly occupied by space, right? Because you have all of the air and everything like that. And then we have all the land in the middle, right? Very much like the nucleus. So you guys see the similarity?
Mm-hmm.
Yeah, okay. So all of the positives charges are in the middle, but we also know that there is the neutrons, which is neutral charge. So the nucleus is made up of the neutrons and protons. And that's going to make up the majority of your mass. Now, a proton is going to weigh 1, a neutron is going to weigh 1. So they're about equal to each other, right? And I should also say this. The way that we've kind of calculated in terms of how things weigh is based upon carbon-12, right? So all of it initially was based upon carbon-12, and that's how we have because if you think about it, weight is relative, right? Is it not?
Yes.
It's a relative factor, something we made up, kind of like money, right? A dollar wasn't always a dollar, right? And if a dollar in the US is going to be different than what it's going to be worth in the UK. So it's all relative, right? And so we need a reference. And carbon-12 meaning the isotope of carbon, 12, that weighs 12, is what our whole periodic table is based upon. So just so you know, you may get a question on that on the exam. Okay, so we talked about those positive particles deflecting. Why do you think they deflected when Rutherford did his experiment? When, it's like, shh. What would cause it to do that?
To do what?
Deflect, bounce off, repel. Oops. Why would Why would positive deflect from something? Something that's positive, why would it deflect from it? Why would it bounce off of it?
Because it's another positive, and positive don't attract, they bounce off of each other.
That's right. So if you have two positives, like have you two ends of a magnet that are the same, you put them together, they kind of push away from each other, right?
Mm.
So that's repel, right? So it repels. So if you have two positive, it repels, where opposites attract, right?
Mhm.
That's where we get that term. You know, when your mom was talking about you dating that bad boy, you know, don't do that, right? And what did you do? You dated him anyway, right? So opposites attract. Two charges that are the same are going to repel each other, okay? So we know that protons, the nucleus, has protons in them, right? Because they're positive. And we put those positive particles, they were bouncing off, so they were repelling. So that let us know that the nucleus was a positive charge. And then also you guys know about the neutrons now, right? So neutrons were basically discovered by James Chadwick. I'm sure that there's a course somewhere about the history of science. I am not a history buff, but I do think it's cool that they've discovered that. And I wish I had as much time as they did to discover things as well too. Drink and talk science, that's what I love doing. And if I could get paid to do it, it would be great. But nobody wants to do that. Okay, so we've talked about electrons, we've talked about protons, but we've talked about protons, neutrons, and electrons. So you guys know what protons and neutrons and electrons are. So what is the charge on neutrons?
Neutral, equal.
Equal or
Neutral.
neutral? Neutral. Okay, so they're neutral. Okay, what about protons?
Positive,
Positive. What about electrons?
negative.
Okay, good. So now I get to tell you about isotopes. Okay, so how are we doing on time?
You're good.
Good.
What-
See, I'm usually at my house, and I'm in my lab right now. My clock has stopped running. It was actually it didn't stop running. It just runs very slow, and according to the time that it was 5 o'clock this morning. So, and then I just reset it when I came in. Anyway, back to this isotopes. So an isotope is two or more atoms that are of the same element, but they have different masses. And you're going to kind of think about this: two or more atoms of the same element, but have different masses. What the hell does he mean by that, right? So like, for instance, I talked about carbon 12. So the way that we would define an isotope of carbon 12, meaning that carbon weighs 12, is we'll put a C, and then superscript on the left-hand side, we'll put a 12. So that tells me the mass of that carbon is roughly about 12 atomic mass units, AMU. Okay. Another isotope would be carbon 13. So that means that we have a carbon that weighs 13. And I'm going to put one more isotope.
I have a question.
Yep.
Would you say that protons and neutrons both weigh kind of the same?
Yep, they're roughly the same.
Roughly, okay, so that's
Yeah.
why mass number is protons plus neutrons.
That is correct. Yeah, they're about 1. Okay, roughly. So a proton weighs, to be almost exact, weighs 0, 0, 0, 8, 7, I believe. I may have one, may be off by 1 0. And then that's for a proton. And then a neutron weighs 0, 0, 0, 7, 9. Okay, so that's the distinction between the two. It's really, really close. Okay, so when we look on the periodic table, do you guys have your periodic table available? Let me pull mine up. So do you see it? See the periodic table?
Yes.
So you see we have carbon 12.011. So that atomic mass represents the average of all of the isotopes that exist in nature, naturally occurring isotopes. Okay, so it's just the average. So what you see on the periodic table will be the average of all of the isotopes that exist in nature. So this lets me know that if you actually look at that number, it's 12.011. So that means that the bulk of all of the carbon in the world is going to be close to carbon 12, right? That's the one that's most commonly observed. Okay, so let's see what that means to us. So this number now, this is called our mass number, right? You notice it's a whole number. We don't say carbon, we don't say 12.00271 or anything like that, right? It's always a whole number, okay? So 12, 13, 14, right? So this carbon has how many protons? So how do we determine the number of protons? I know we talked about this.
Half of the mass number?
Nope, not the mass number. Number of protons. So, nope, it's not 12. Our atomic number here, so if we look up the number at the very top here, located here, we have 1, 2, 3, 4, 5, 6, 7. You notice how you have those numbers that are there? They're not just there to tell you that's 1, 2, 3, 4, 5, 6, 7. They're to tell you what that atom is. So carbon is always going to have 6 protons, right? So the atomic number is going to be equal to the number of protons. And I bet you if you guys look back at your notes, you'll see that we've talked about this. Oops. Okay, so your atomic number is going to equal to your number of protons, okay? So your atomic number also defines the element. That tells me that 6, atomic number 6 is always going to be carbon, because carbon is always going to have how many protons?
6.
6. It's never going to change. The number of protons is never going to change for an element. Always going to be that number, okay? So now I want you to think about this. So Jennifer said something about the mass of an atom is composed of the protons plus the neutrons. So if carbon 12 weighs 12 and it has 6 protons, how many neutrons must carbon 12 have?
6.
Okay, so we have 6 protons, 6 neutrons. And we know that elements on the periodic table, they're always going to be neutrally charged, right? Because they're elements on the periodic table. So how many electrons have to balance out the number of protons? For carbon 12.
Six.
That is correct. Okay, because if we have 6 positive charge, because we know that protons are positive, how many negative charges must we balance them out with? Simple?
Yes.
Okay, so you'll see these letters. Atomic number, the symbol for atomic number is Z. Often we'll use N for number of neutrons, and A for number of protons. I'm sorry. Sorry, not A. A for the mass number, which is this number up here. So protons will be the same as your Z. N, it's going to be your number of neutrons, capital N. Okay, and we know that your protons and neutrons have to be balanced out if that atom is neutral. Okay, so now that we've talked about that, let's see, what can we do? Let's talk about carbon-13. How many protons does carbon-13 have?
6.
Okay, how many electrons does carbon-13 have?
6 electron.
Okay, then how many neutrons does carbon-13 have?
7.
And how did you get that number? 7.
Since the mass number, which is the 13, needs to equal the addition of the neutrons and the protons. So we just subtract the 6 protons from the 13, and then we get our 7 neutrons, because basically they're close to weight, like I think Jennifer was saying.
Yep.
Or mentioning.
That is correct. Okay, so what about carbon-14? Number of protons.
6.
Number of neutrons.
8.
Number of electrons.
6.
Okay, piece of cake?
Yeah.
Okay, let's see if we can make it a little more challenging. You know, that's too easy, you know. Okay, so let's see. Let's pick tungsten. Okay, so we're gonna say tungsten. Tungsten 190. Okay, so what is the mass number for tungsten 190?
$190.
190. What is the number of protons?
74.
Number of neutrons?
116.
Number of electrons?
74.
Atomic number?
74.
Atomic mass?
Is that 192?
It's 190. Yes, that is 190 also. I thought you said
Yeah.
192.
Oh, no, yeah.
Yeah, you meant also, yes. Okay, piece of cake. I know we ran out of room. Okay, you feeling confident? Yeah, good, good, good. Anybody not getting it?
For the atomic mass,
Yep.
how did you guys get 190?
Because the mass number tells us the new mass of that particular isotope. So the isotope weighs 190, right? So if I just gave you tungsten, if I wanted to know about tungsten in general,
Mm-hmm.
because that's an average, so let's just do tungsten in general. So that's going to just give me the atomic mass will be the number that's written on our periodic table. But in this case, you're not worrying about the average of all the isotopes. You're worried about just one isotope. And that one just weighs 190.
Okay, just because the.
Yeah.
Gotcha.
Okay.
Yeah, the mass is 190. Okay, gotcha. So if it was mass number like 170, let's say,
Yep,
then the atomic mass would still be 170.
that is correct. Yep.
Okay, gotcha. Just because it's an isotope.
Yep.
Okay, thank you.
Okay. Okay, let's see. Oops. Okay, so this is just telling you everything that we just talked about. And it gives you the definition, the textbook definition, okay? So there are two ways of showing it. One was the one where I showed you that you would talk about isotopes. So one way you don't actually have to put the atomic number down here, which is just the number of protons. Most cases, they just write it just that letter, just the mass number up top, and that's it. But when you're talking about nuclear chemistry, because it gets a little more complicated, they want you to sit there and include that. But for right now, you can get away with just putting it as the subscript for your mass number and not worrying about putting the atomic number down below. This is one way that we would write carbon 12 to let us know that it's the isotope that we're talking about. So just write out the carbon-12. Sometimes you'll see just the symbol C-12. That'll also mean the same thing. And I like telling you that because, like you'll read an article in the news and they'll be talking about, uranium-97, right? And they'll put U-97. And so now you know exactly what they're talking about. It's an isotope. Okay, so let's see, how many of you are there? Ooh, I'm hot. So there's, 13 of you guys? I'm going to put you guys in groups of 3. I want you to fill out this table. Do you think you can handle that? How long do you need? 2 minutes? Now, the rule is that if you guys go in groups, you got to communicate. Right, Kel? Okay, everybody back. Yep. Okay, group 1 or room 1. Bernardo, Brian, Jennifer, and Jetsamini, right? Did I mess that up? Are you guys there?
I'm here. Jennifer here.
Jetsamini, are you there?
She was. Maybe she's in the bathroom. I don't know.
Okay. Well, group 1, you guys do barium.
Okay.
Let's see. Brian and Hector, you guys do oxygen, the second one. Let's see. Alexandria and Norma, you guys do the third one, the third row. And then Alan, Kevin, and Steven, you guys do the last row.
Okay, you just want us to like write
it up?
in the, oh, oops. Sorry. Okay, you got it.
Okay, let's see. First one's hard to see.
Is that better?
Yeah, it's a little bit better. It's just the green on blue.
Oh, it's blue. It looks purple on my screen.
Oh,
Well, if you want, I could just. So the element symbol, I wrote Ba for barium,
uh-huh.
and we got the atomic number 56,
Okay.
proton number 56, neutron number 82, mass number 38, and then the nuclear symbol is already written in there, and then the name of the isotope, we got barium hyphen 138.
Okay. Piece of cake. Everybody agree or disagree?
Our group agreed.
So that mass number. Okay, so I have questions. I have a lot of questions. It could be because I'm blind.
Oh shoot, mass number is 138. I accidentally deleted the 1. Sorry. That's probably what your question was, right?
That was my question, yes.
There we go. Sorry.
That's right. Okay, let's see, group 2. You guys didn't finish. Brian and Hector. Are you guys
Yeah, I
there?
wasn't sure about the rest.
We weren't unsure.
Yeah.
We were unsure about the.
Okay, so what do you guys think is going to be up in the superscript on the left-hand side? And why did you choose a mass number of 16?
Would the mass number be, do you want them to answer?
Well, we'll work as a team. We can work as a team. You said
Okay.
what the mass number would be what? What do you think it's going to be, Jennifer?
18.
So how did you get 18, Jennifer?
You add the neutrons and the protons together to get the mass number.
Okay, you guys got that, Brian and Hector? So the sum of your protons plus your number of neutrons.
It's because we forgot to close it in. That's why.
Oh, okay.
Oh.
So you get to fix it because you guys are doing the writing. I'm just here to look pretty. That's my job. And you guys don't show yourself, so I can't tell if you guys are pretty or not. Okay, good job. There we go. Okay, so then what is going to be my nuclear symbol then?
The mass total over the proton total with the element symbol.
Okay. Okay, guys, you guys got that?
Yes.
Okay, so you guys going to put it on the board for us, so we'll be able to get that too.
All right.
Okay, and then it says the name of the isotope. So what would we call it, guys?
It would be oxygen hyphen 18.
That is correct. And Jennifer, I didn't know that you were a guy. I'm glad I'm learning that.
They're not answering. Sorry.
That's all right. Sometimes we got to give them an opportunity to think, right?
Gotcha.
Yeah. We're not all naturals. Okay. Ladies in room 3. Are you guys ready to finish up? Or do you want the guys in room 2 to help you?
I could finish it up. My computer just wouldn't let me write.
Okay. Okay. Yes. Dictate for me. And I'll write for you. Let me guess. You have a Chromebook, right?
Yeah.
Yeah.
So for the nuclear symbol, it would be 206/82, and then the what's it called? The element would be a PB.
Hold on. I have a little trouble writing myself. You said PB,
Mm-hmm.
and you said 206/82.
Yes.
Okay.
And then the name of the isotope would be lead-206.
Okay. Oops, if I could spell lead. It's one of those days. Okay. Piece of cake. And the last
Yes.
one. What was that? Somebody broke up. Yes? Yes? No? Maybe? Okay. Okay, so. Okay. So how you feeling on everything right now? Did that help? Brian and Hector?
Yes, it did.
Yeah. And you know who to contact if you have a little extra help, you need a little extra help. Jennifer there, you know, she's willing, right?
All right.
Okay.
Yeah. Sorry about that, Professor.
No, that's okay. No, I don't mind. That's what I want. I want you guys to help each other, right? Because I'm only one guy, and your class altogether with the 2 sections, you guys are what? And I took more than what I was supposed to take to try to get you guys all in. So I have about 67-ish of you guys in your section alone. Then I have the other section, and that one is about 67-ish as well. So that's 120 students, and there's only one of me. So if you guys can help each other out, that helps me out. So I'm not trying to task you, but I just want to make sure that they get a chance to answer. That was my only thing. I'm just giving you a little bit of a hard time. Now I have a question. Are you and Alexandria related? You guys have the same last name.
Not that I know of, unless she's a cousin of mine that I've never met.
Okay. Total aside, I just thought I'd ask. Okay, so how are you guys feeling about the material? Because it's going to be, the way it works is, okay, so this is just your foundation, right? This is that cement layer at the bottom. That's what we're building. Now, if that cement layer at the bottom is weak and it has cracks in it, what happens to that building?
It crumbles down.
It crumbles. Do you guys want to crumble?
No.
No, we want to be able to continuously build, right? So you want to make sure that you get this foundation down, okay?
Okay.
Okay. Okay, next time I expect you to have coffee, be energetic, be jumping up and down.